Yes. Hello students. Welcome to the session. Before starting today concept, yes, let me introduce myself. Yes, students, my name is Surendra Babu. For 10 years, I am educating the students for GATE, ESC and PSUs in the field of electrical and electronics engineering. Yes, students, these are the subjects I am teaching for GATE, ESC and PSUs for electrical, power electronics, power systems, electrical missions, electrical and electronic measurements. Sir, whatever the core subjects are there for electrical students, all the core subjects I am teaching since 10 years for GATE, ESC and PSUs. And this subject I am teaching for instrumentation students. This also one of the core subject for instrumentation students. That is the transducers and mechanical instrumentation. Students, apply my promo code BABU10, get the 10% discount on Unacademy Plus subscription. You get the 10% discount on Unacademy Plus subscription. If you go for Plus subscription, apply my promo code BABU10. And also use my promo code BABU10 to unlock our Unacademy learning app. Yes, students, this is about me. Now come to our Unacademy subscriptions. Yes, sir, there is a Plus subscription and Iconic subscription, sir. Sir, if you select the Plus subscription, these are the benefits you can get, sir. Live classes, crash courses, weekly tests, doubt solving sessions, that is in both English and Hindi, sir. Sir, these are the benefits you can get if you select the Plus subscription. Sir, what are the benefits if you select the Iconic subscription? Yes, students, along with Plus subscription, if you want this extra benefits means, then select the Iconic subscription. Yes, sir, personal coach is there, study planner sessions, study booster sessions, personalized test analysis, preparatory study materials. That means along with Plus subscription, if you want this extra benefits, then go for Iconic subscription, sir. Okay, this is about our Unacademy Plus subscription and Iconic subscription. Yes, students, now concentrate, sir, how to get our Unacademy learning app. These steps you follow in order to download our Unacademy learning app, sir. Search Unacademy learning app in our Play Store. Then that is the first step, sir. Step 2 is install the app. The third step is, sir, select your goal. That is, manage your goal. Our Unacademy is providing various courses, sir, in order to crack different competitive exams. Now you are in GATE and ESE. Then select the GATE and ESE, sir. Then select the Plus. Get the subscription, sir. Then after completing subscription, to unlock the app, use my promo code BABU10, sir. These are the steps you follow in order to get your Unacademy learning app, sir. Yes, sir. Then what are the course fee details for Plus subscription, sir? This I am giving for GATE and ESE for 1 year program, sir. That is for 12 months program. For 1 year, that is 12 months program. Apply my promo code BABU10, get the 10% discount. After 10% discount, you pay only 27,225 rupees only. Sir, this is for GATE and ESE, sir. 2 courses for GATE and ESE for Plus subscription. This is for 1 year program. Sir, this is also for Plus subscription, but it's a 1.5 year program, sir. It's an 18 months program for both GATE and ESE. Apply my promo code BABU10, get the 10% discount and you pay only 34,650 rupees, sir. Yeah, these are the course fee details for GATE and ESE for Plus subscription for 1.5 year. Yes, sir. This also for Plus subscription for GATE and ESE. It's a 2-year program, students. It's a 2-year program. Apply my promo code BABU10. Get the 10% discount and you pay only 39,600 rupees, sir, after 10% discount. Yeah, this is a 2-year program. Yes, now come to the Iconic subscriptions. Then what are the course fee details for Iconic subscription? For 1 year program, that is for 12 months, apply my promo code BABU10, get the 10% discount and you pay only 45,225 rupees. Sir, this is also for Iconic subscription for GATE and ESE. Sir, this is for after 10% discount, this is the payment. Sir, this is also for Iconic subscription for 2-year program. It's a 24 months, that is a 2-year program, sir. Apply my promo code BABU10, get the 10% discount and you pay only 66,600 rupees, sir. Students, these are the course fee details for Plus subscription and Iconic subscription, sir. You know what are the benefits if you select the plus subscription? Not only live classes, so many benefits are there, sir. Then if you select the iconic subscription, that extra benefits, what are in the large circle that I shown in the last slide, sir, previous slide, sir. Okay, that is the extra benefits we can get if you select the iconic subscription. Yes, students, you please concentrate. Sir, these are the plus batches taken by the top educators for electrical and ECE, sir. And these are the batches running for target ESE prelims 2021 batch, rank booster batch for GATE 2021, target ESE prelims 2021 batch for electrical, sir. This is electrical, this is for ECE, and this is for electrical, sir. And this is rank booster batch for GATE 2021 for electrical, sir. You please concentrate. These are the top educators who are teaching in plus batches. Yes, students, this is our Unacademy GATE Telugu December month schedule, sir. Yes, sir. These are the subjects are running in December month schedule. You please concentrate along the timings it is given, sir. Electrical missions, engineering, mathematics, power systems, aptitude, along the timings it is mentioned. You please concentrate, sir. This is crash courses, subjects, power electronics, EDC and aptitude, sir. You please concentrate our crash course subjects also. Yes, sir, Unacademy Combat 2, sir. After successful of Combat 1, now we are going for Unacademy Combat 2, sir. You please concentrate. Enroll for free. Next combat goes live on December 29, 6 p.m. sir. Register now. And there is we can win the exciting prizes by participating in combat, sir. Yes, students, this is eval for GATE 2022. This is eval for GATE 2022. Already the batch started on 21st December, sir. Already started. You please concentrate for EE GATE. Then during subscription, apply this code, sir. EE GATE turn. This is for electrical batch, sir. And this is eval for GATE 2022. This is for ECE, sir. Then already the batch is started on 21st December. You please concentrate. This is English and Hindi, sir. This language is English and Hindi. Apply. You can apply the code ECE GATE 10, sir. Sir, this is a free special class series. Know your basic for GATE 2022 and 2023. Sir, you please concentrate. Students, free special class series. It is a free special class series. A complete roadmap to approach each subject of every branch. Very, very important. You please concentrate. See, once you want to crack any competitive exam, the basics are very important, sir. Basic fundamentals are very important. You please concentrate. Who are the aspirants for GATE 2022 and 2023? Students, you please concentrate. This is for every branch. This is for every branch. Mechanical engineering, civil engineering, electrical engineering, ECE. That is CS and IT and chemical engineering. For every branch, there is a free special class series. Know your basics who are preparing for GATE 2022 and 2023, sir. You please concentrate. Yes, students, all of you, good evening. Come to the today concept. Yes, sir, all of you, good evening. Yes, students, it's a very important topic for GATE point of view and even for ESE point of view also. Today concept is very, very important. Yes, all of you, good evening. Yes, sir, please inform to your friends. It's a very important topic. That is in fault analysis, three-phase short circuit analysis on transmission lines, sir. This I'm discussing what is the short circuit analysis, what are the calculations of short circuit currents on a transmission line under no load conditions. Particularly, I am giving this analysis for under no load condition. We are assuming that there is no load on the transmission line. With that assumption, I am explaining this concept, sir. Yes, students, all of you, good evening. Yes, see that today concept. I am going to explaining what is the three-phase short circuit analysis on no load operating transmission line. It's a no load operating transmission line, sir. Here, in order to do this analysis, there is some assumption, sir. With this assumption only, I am doing this analysis. The line is fed from a constant AC voltage source, sir. With this assumption, I am doing this analysis. Whatever the AC voltage we are giving, we are assuming that it is a sinusoidal AC voltage and assuming that it is a constant AC voltage, sir. That's the first assumption. The second assumption is short circuit takes place when the line is unloaded. Even under the loaded condition is also there is a faulty calculations, short circuit calculations are there. But here I am assuming that there is a short circuit takes place when the line is unloaded. Unloaded in the sense it is under the no load conditions, sir. This is the second assumption. Line capacitance is negligible, sir. Even though I am calculating the short circuit analysis on no load operating transmission line, but I am assuming that the line capacitance of the transmission line is neglected. With that assumption, I am doing this analysis, sir. And once the capacitance is neglected, it is represented by a lumped RL series circuit, sir. Whatever the circuit I am assuming in the case of analysis of short circuit currents, it is a lumped series circuit. I am assuming that it is a lumped series circuit, sir. I am neglecting the capacitance. With this assumptions only, I am doing the three-phase short circuit analysis on no load operating transmission lines, sir. Yes, students, you please concentrate. Let us consider. I am assuming that it is a short circuit. Let us assume that a transmission line. It is a transmission line, but it is a no load. Let this is the bus. Here we are giving the some supply. Let it is connected to the alternator or generator. Let it is connected to the alternator or generator. This is some source. I am using this is the AC source. This I am assuming that AC source. AC source is one of the alternator or synchronous generator. It is the AC source. Let assuming that is an ideal case. Ideal AC source. I am assuming that it is an ideal AC source. Let there is a three-phase short circuit fault is occur. A three-phase short circuit fault. A three-phase short circuit fault is occur on the line. Assume that all the three-phase lines are balanced. Then once all the three-phase lines are balanced, then you consider only for per phase. Assume that all the initial before short circuit, assume that all the three-phase lines are balanced. If it is a balanced means we can analyze for one phase. We can analyze for one phase. A three-phase short circuit fault means it is a balanced. After three-phase short circuit fault also, system is under balanced condition only. That point I already told that. That's why I am analyzing for only one phase. If it is analyzed for one phase, then for remaining three phases directly we can write. Remaining two phases we can write directly, sir. Understood? Let reference is A phase. Let reference is A phase. We are assuming that reference is A phase, sir. Our reference is A phase. And it is a balanced system. And assume that it is a balanced system. It is a balanced system. It is balanced system. And we are assuming that reference is A phase. Then the per phase equivalent circuit is represented as, I neglected the capacitance, sir. Then the per phase equivalent circuit with respect to RL parameters. Okay, this is the per phase equivalent circuit, sir. Okay, this is the per phase equivalent circuit. Let this is R. I told that the assumption is we are representing these parameters as a lumped parameters. This is RL. Let there is some switching operation. And there is short circuit fault is occur on the transmission line. A three-phase short circuit fault. Okay, this is per phase equivalent circuit. The per phase voltage, I am taking the reference is A phase. Then you take this is Vm sin omega t. You take this voltage is Va is, you take Vm sin omega t plus alpha, sir. You take this is Vm sin omega t plus alpha, sir. Where alpha is the switching angle for that is whatever the alpha is there, where alpha is the switching angle, sir. We are assuming that alpha is the switching angle. Where alpha is the switching angle. Yes, students, you please concentrate. It is a per phase equivalent circuit, sir. That's why it is a per phase voltage. It is a per phase voltage. Because a balanced system, we can analyze for one phase, then remaining two phases directly we can write. This is R and this is L, sir. Now let us assume that the switch is closed at t equal to 0 plus, sir. Let there is a short circuit fault is occur. On this line there is a short circuit fault. This is the short circuit fault. Let this is IF. There is a short circuit fault, current is flowing. Yes, sir. These are the assumptions. With this assumption, I am drawing the circuit like this. Even though it is a transmission line, I am not considering any line capacitance. That's why I am not considering any line capacitance and assume that these parameters are represented as a lumped parameters. This RL, that means the line is having the resistance and the inductance. With that assumptions only I am explaining, sir. Yes, students, you please concentrate. What is the analysis? If the switch is closed at t equal to 0 plus. Yes, sir. This is the per phase equivalent circuit. This is a per phase equivalent circuit of transmission line. Let this R is the line resistance. L is the line inductance. L is the line inductance. Yes, sir. Then there is some switch arrangement. Let a three-phase short circuit fault is occur on the line. A three-phase short circuit fault is occur. Then the fault current is, I am assuming that this is IF. IF is the fault current. Then what is this per phase voltage, sir? This per phase voltage is Vm sin omega t plus alpha, sir. This I am representing like this. The per phase voltage Va equal to, this is Vm sin omega t plus alpha, where alpha is the, sir, what is the alpha given? This is a switching angle, sir. Let the switch is closed at t equal to 0 plus. When the switch is closed at t equal to 0 plus, then there is a fault current, sir. Let this fault current is IF, where small if is indicate the, small I indicates instantaneous value of fault current. That is the meaning. Let, yes sir, you please concentrate. Let at t equal to, whatever the formulas I will give in this analysis, that is very important for any competitive exam, mainly for GATE and ESE, sir. Let at t equal to 0 plus, switch is closed. The switch is closed. Switch is closed, and assume that if the fault occurs at t equal to 0 plus, that is this is switch is closed, and assume that the fault is occur at t equal to 0 plus. Fault is occur at t equal to, instead of switch is closed, I am assuming like this, sir. You please concentrate. Yes. Let at t equal to 0 plus, fault is occur. At t equal to 0 plus, fault is occur. Fault is occur. Or at t equal to 0 plus, we are closing the switch. Let the source voltage is phase voltage. This is Va is the phase voltage, sir. I am assuming that Va is the phase voltage. I am taking the reference is the A phase voltage, sir. Then what is phase voltage, sir? The phase voltage Va equal to Vm sin omega t plus alpha, sir. Vm sin omega t plus alpha. Yes, sir. Now apply the KVL for this loop. The switch is closed at t equal to 0 plus. Let us assume that the fault is takes place at t equal to 0 plus. Then there is a fault current. Then apply the KVL for this loop, sir. Apply the KVL. Then what you can get? This IF into R plus L into DIF by dt, sir. L into DIF by dt is equal to how much, sir? This is Va. What is that Va? Vm sin omega t plus alpha. Vm sin omega t plus alpha. Now we want to find the solution for this equation, sir. We know that this is having the, after finding the solution for this equation, it is having the two components. In the AC analysis, the basics of AC analysis, you know this one, sir. Directly I am giving by finding the solution for above equation. By finding the solution for above equation. Sir, what it consists of? It consists of two components. The solution, the fault current IF equal to, it consists of two components, sir. One is a transient current, another one is a steady state current, sir. One is transient current, another one is steady state current. Actually, you find this solution for this one is particular solution and complementary solution, sir. By finding particular solution and complementary solution, you know how this simplifying differential equations. Then IF equal to ITR plus IS. That means it consists of transient component. It consists of transient component. That means if you find the solution for that equation, it consists of transient component, and it also consists of steady state components. Steady state component. It consists of two solution, that is a two component, transient and a steady state component. Sir, what is the transient component? The ITR is given as, correctly I am writing this one, sir. The transient component ITR equal to some constant k into e power minus t by tau you can get, sir, where tau equal to L by R. This is the time constant where tau equal to L by R. Okay, this is the transient component we can get by finding the solution. Then what the steady state component we can get, sir? Then if you find the what is the steady state component, the steady state component ISS equal to, we can get Vm by Z, Vm by Z sine of omega t plus alpha minus theta we can get, sir. Yeah, this is the steady state components. Sir, what is omega, what is theta here, sir? What is the Vm by Z and what is the theta here, sir? We know this one. What is this circuit, sir? It is RL circuit. It's a RL circuit. Yes, this is R and this is the L. Let the fault current is IF, sir. In this RL circuit, how to write Z equal to, sir? Z equal to, that is R plus JXL. R plus JXL. Then how to write theta equal to? Theta equal to tan inverse XL by R, sir. This theta equal to tan inverse XL by R. This minimum basics you know. This I am writing. What is theta here? Theta is the impedance angle, or for RL circuit it is a power factor angle. Theta equal to tan inverse XL by R, sir. Then where Z equal to R plus JXL. Then you write as a magnitude means square root of R square plus XL square we can write, sir. Okay. Now this is the steady state current in this circuit. What is the steady state current is? Vm by Z into sine of omega t plus alpha minus theta, sir. Now what is the total current? This is which current, sir? This is the steady state current. Then what is the total current? IF equal to, then ITR, transient current plus steady state current, sir. Then this IF, the total fault current IF equal to, what is the transient current? K into e power minus t by tau, sir. Plus what is ISS, sir? Vm by Z into sine of omega t plus alpha minus theta, sir. Omega t plus alpha minus theta. Now if you want to find exact solution for IF, now I want to find the K value, sir. To find the K value, apply the initial conditions, sir. Apply the initial conditions. Actually, we are assuming that at t equal to 0 plus switch is closed, and at t equal to 0 plus there is a fault takes place. There is a short circuit fault takes place. We are assuming that at t equal to 0 plus switch is closed, and there is a at t equal to 0 plus a short circuit fault takes place, sir. That means before 0 plus means you take at t equal to 0 minus, sir. Then to find K value, apply initial conditions. To find K value, where K is the constant, sir. To find K value, apply initial conditions. Apply initial conditions. Yes, students, you please concentrate. Apply initial conditions. Then if you apply the initial conditions, then at t equal to 0 minus, at t equal to 0 minus, that means before closing the switch, at t equal to 0 minus, what is fault current, sir? We are assuming that fault takes place at t equal to 0 plus. But at t equal to 0 minus means what is IF of 0 minus, sir? 0. Still fault is not takes place. That fault current equal to 0, sir. At t equal to 0 minus. But you know that at t equal to 0 plus, at t equal to 0 plus you want, sir. At t equal, because fault takes place at what conditions are? At t equal to 0 plus. At t equal to 0 plus means, please students, you concentrate. But you know that IF of 0 minus equal to IF of 0 plus. You studied in the transients. 0 minus equal. But what is IF of 0 minus, sir? That is equal to 0. Then you substitute at t equal to 0 plus. IF of 0 plus equal to 0, sir. Then you substitute that this 0 equal to this t equal to 0 means e power 0, sir. This e power 0 becomes 1. Then k plus Vm by Z. Yes, students, please concentrate. Vm by Z sine of omega t plus theta minus alpha, sir. Omega t plus theta minus alpha. Then what is the K value, sir? K value equal to minus Vm by Z. Please students, you please concentrate. Minus Vm by Z sine of omega t plus theta minus alpha, sir. Then from this, what is the K value you can get? then k equal to, the value of k equal to, you bring that negative, the negative is into the function. What you can get, sir? Vm by z. This is Vm by z. This k value equal to minus, sorry, 1 minute, sir. You please concentrate. I substituted what is t equal to 0, sir. This also becomes 0. T equal to 0 means this term is also becomes 0. Yes, sir. Yeah, this is 0. That is 0 plus theta minus alpha. Then what you can get? K value equal to, K value. Sir, what is the K value you can get? Sine of theta minus alpha. Minus Vm by z. Sine of theta minus alpha. But I want k, sir. This k value is, you bring this negative term. You bring this negative term into the function, sir. What you can get? Vm by z into sine of alpha minus theta. Vm by z into sine of alpha minus theta. Now you substitute this k value in this equation, sir. You substitute this k value here, sir. Substitute this k value here. Then what is the fault current you can get, sir? What is the fault current you can get? Yes. This is the exact solution for fault current. The fault current IF equal to, yes, sir, Vm by z. Vm by z. Sine of alpha minus theta. Sine of alpha is, sir. What is this value, sir? We are getting sine of alpha minus theta. Sine of alpha minus theta e power minus t by tau, sir. What is tau, sir? That is L by R. The time constant is for RL circuit is L by R. Plus Vm by z into, yeah, this you take the magnitude, Vm by z into sine of omega t plus alpha minus theta. Yeah, this is the solution for fault current. If any short circuit fault takes place on a transmission line, yeah, this is the solution we are getting. This is the exact solution. IF equal to, yes, students, you please concentrate. Vm by z into sine of alpha minus theta e power minus t by, sir, it's a alpha minus theta, theta minus alpha. You please concentrate. This is sine of alpha minus theta. This is also sine of alpha minus theta. Yes, sir. It's a sine of alpha minus theta. Yes, this is sine of alpha minus theta. Here also sine of alpha minus theta. Then this is minus, this is theta minus alpha means this is sine of alpha minus theta, sir. Okay, this is sine of alpha minus theta. Then if you multiply with the negative sign function, then it becomes which one, sir? Sine of theta minus alpha. Sine of theta minus alpha. Okay, this is the k value, sir. Then after substituting that k value, what you can get? Yes, sir. Sine of theta minus alpha. Okay, this is the exact solution, sir. Sine of theta minus alpha. That is sine of theta minus alpha into e power minus t by tau. That is Vm by z sine of omega t plus alpha minus theta. This is the exact solution for example. If you want to write in terms of, theta minus alpha means you bring the minus is common. Yeah, that is no problem here. Vm by z into sine of theta minus alpha. This I am writing exactly. That is sine of theta minus alpha. That is e power minus t by tau Vm by z into sine of omega t plus alpha minus theta. Sir, what is this component, sir? This component is the transient components. What is this component, sir? This is which components are steady state component. Okay, this is the transient component. This is the steady state components. This is also called, sir. Yes, sir. This transient component is also called, very important, sir. You please concentrate. Exponentially decaying signal because of e power minus t by tau. Exponentially decaying signal or decaying term. Exponentially decaying terms. Or it is also called, it's a DC offset current, sir. It is a DC component of fault current. DC component of fault currents. DC component of fault current. Yes, students, you please this is a DC component of fault currents. Sir, what about this one? This is the sinusoidal component. This is the sinusoidal component. What is this component, sir? This component is sinusoidal component. Sinusoidal component. Or it is also called, steady state component, sir. It is a steady state component. It is a steady state component. or it is also called sustained short circuit current component. Sustained short circuit component, short circuit current component, short circuit current components, short circuit component current. Yes sir, short circuit current component, or it is also called AC component of fault current. It's a not DC component, it's a AC component of fault currents. Different names. AC component of fault currents. Yes, students, you please concentrate. But what about this one, sir? It is a DC component of fault current. It's a DC component of fault current, sir. Yes, it is a DC component of fault current, but it is a AC component of fault current. But point to remember, without any DC offset current, without any DC offset current, it is a DC component of fault current. If you consider only this term, sir, it is a symmetrical component of fault current. It is a symmetrical. It is a symmetrical component. It is a symmetrical component. Only DC is considered. Only steady state component is the symmetrical component of currents. But after adding this DC component with the symmetrical component of current, this total fault current, sir, this total fault current, whatever the total fault current is there, total fault current, the total fault current is the asymmetrical current, sir. It is the asymmetrical current. Sir, why it is asymmetrical current, sir? The total fault current is the asymmetrical current, sir, because it is a combination of DC plus, that is a DC current plus AC current. It is a combination of DC current plus AC current, sir. That's why this total, the resultant fault current becomes a asymmetrical current, sir. Why the resultant fault current becomes a asymmetrical current, sir? Because of the DC current. Because of DC component of current. If this DC component of current is added to the symmetrical component of current, the total fault current is becoming which current, sir? It is asymmetrical current. Because of this DC current is added to AC current, then automatically this becomes a asymmetrical fault current. It becomes a asymmetrical fault. Yes sir. Okay, this is the calculation of fault current if any short circuit fault is occur on a transmission line. So very important, sir, that you concentrate. What you are getting? Vm by Z into sine of theta minus alpha, where theta is the angle because of the RL, sir. Impedance angle or power factor. Impedance angle, that is because of R and L, sir. R and L. That is the transmission line. Okay, where R and L is the line parameters. This e power minus t by tau, what is the tau here, sir? Tau is the L by R, that is the time constant. This Vm by Z into sine of omega t plus alpha minus theta, sir. What is the alpha here, sir? That is the switching angle. Where alpha is the switching angle. Theta is the angle because of the R and L parameters of the transmission line. Yes, sir. You please concentrate. Yes. Now, this component, if you consider only this component, sir, if you consider only this component, it is a symmetrical component. But if you consider only this component, sir, it is a DC component. By adding this DC component and symmetrical component, it becomes which one, sir? Asymmetrical current. So that means the main reason for asymmetrical current is in the case of three-phase short circuit fault of a transmission line is because of which component, sir? DC component of current. Sir, one more point to remember. In this total fault current, only this symmetrical component of this AC current only causes the power loss, sir. But what the power loss due to this DC component is zero, sir. And it is exponentially decaying term or DC component of fault current, sir. And it is not a sustained, short circuit current, sir. It is a momentary short circuit current. It is a momentary current, sir. That means it can't exist for long time. Only it exists for 2 to 3 cycles or 1 to 2 cycles only. Up to below 5 cycles only it can exist, sir. Below 5 cycles only. Up to 5 cycles only it can exist. Or below 5 cycles only it can exist. After 5 cycles is completed, then at 5 cycles are completed, this term will becomes to 0, sir. Then it consists only which current, sir? Symmetrical component of current. That's why the name is given as a which current, sir? Momentary current. It is a transient current. It is a momentary current. But it is a which current, sir? Sustained short circuit current, sir. Sustained short circuit current means after clearing the short circuit fault also, then which component will present, sir? Vm by Z into sine omega t plus alpha minus theta, sir. That's why it is also called symmetrical component of current. If you consider only this current. Yes, students, you please concentrate. Yes, sir. Now we'll see what are the calculations based on this analysis. Here I am giving the waveforms, sir. These are the waveforms of short circuit current on transmission line. These are waveforms of short circuit current on transmission line. Okay, this current waveform, sir. This one is the current waveform. This is the steady short circuit current. Steady short circuit current. But I drawn this waveform with respect to voltage, sir. This waveform is phase voltage waveform, and this is the current waveform. This is the current waveform. Then what about this angle, sir? This angle, generally this angle is taken as a, this is the theta minus alpha. Yeah, this is a, you take this angle is the, this angle is taken as a theta minus alpha, or you take alpha minus theta. It's a theta minus alpha. This is the theta minus alpha. Okay, this I am giving this. Please concentrate. Generally, this angle is measured as this one, sir. Okay, this angle is measured as, it's a theta minus alpha. Okay, theta minus alpha. Then this is with respect to source voltage. I drawn this current waveform. This waveform is the current waveform. But this is which waveform, sir? That is a VA. That I represented with, that is a, this is a phase voltage waveform. This is a phase voltage waveform. Then what is the nature of the steady state current, sir? The nature of the steady state current is which one, sir? Sinusoidal current. The nature of the steady state, this is the steady state current, sir. The nature of the steady state current is what nature? It is a sinusoidal nature. It is a sinusoidal nature. The nature of the steady state, it's a sinusoidal nature. And this is the voltage, sir. But this current is lagging with the voltage. The current is lagging with the voltage. Generally, what is this one, sir? We are getting steady state current ISS equal to Vm by Z into sine of omega t plus alpha minus theta, sir. Alpha minus theta. But alpha minus theta. This is alpha minus theta. This component, you know. Yes, sir. This is alpha minus theta. Now I am taking this minus is common, sir. This is Vm by Z into sine of omega t. Take minus is common, sir. It is a theta minus alpha. It is a theta minus. That means this angle is theta minus alpha. With respect to sinusoidal, Vm by Z sine, with respect to Vm sine omega t, this current component is lags by angle of how much, sir? Theta minus alpha. Sir, I am taking this is minus is common here, sir. If you take minus is common, then this alpha minus theta is written as a theta minus alpha. Once it is written as theta minus alpha means this is the current, the steady state current with respect to phase voltage lagging by angle of how much, sir? Theta minus alpha. It's lagging by angle of theta minus alpha. Okay, that is the observation. Next, this is the DC component of current, sir. You please concentrate, students. This is the DC component of current. This is the DC component of current. I told already, it is a exponentially decaying current. It is exponentially decaying current. Then after some time, this component will goes to zero. This component, that's why it is a momentary current. It can exist only for few cycles only. After few cycles, then it goes to zero. But point to remember, during subtransient period, what is subtransient period? I will give. During subtransient period, this DC component of current is more decaying, sir. More decaying. During which period it is more decaying? During subtransient period, it is a more decaying. Then slowly it is decaying and it completely falls to zero. But this can exist for maximum how many cycles it can exist, sir? Up to 5 cycles it can exist, sir. Up to 5 cycles. Then after 5 cycles, it completely falls to zero. Okay, this is the DC component of current. I already given in the analysis, sir. That means once the fault takes place, there is a two components. One is DC component of current, another one is AC component of current. But this AC component of current is exists even the fault is clear. But this that means continuously that AC component of current is exists. But which component will fall to that is this whatever this DC component of current is there, that is offset current or DC offset current exists only few cycles. Now if you combine this, all these two currents are added, sir. What the resultant fault current, sir? The resultant fault current is this one and this one, sir. This is steady state current plus transient current. Yeah, this is the transient current, sir. This current is the transient current. This is the transient current. By adding these two, then we can get the resultant current. That resultant current is which one, sir? Asymmetrical fault current. That resultant current is nothing but which current, sir? It is asymmetrical fault current. Yes, students, you please concentrate. Now, this is the waveform of a short circuit current on transmission line, sir. Okay, actually, this is which current, sir? It is a steady state current, sir. It is a steady state current. Now, this is which current, sir? It is a DC offset current. Okay, this is ISS, sir. This current is ISS. Please, students, you please concentrate. Very important concept. It's a steady state come. Then what is this current, sir? It's a transient current, sir. This current is the transient. Now adding these two, sir. When I added these two, this current and this current is added. Now I am getting the waveform like this, sir. When these two currents are added, I am getting the waveform like this. This is the waveform. Okay, this is the resultant fault current, sir. Okay, this is the resultant fault current waveform I am getting by adding this DC offset current and a steady state current. Students, please concentrate. By adding these two currents, sir, what the current I am getting, sir? That is the asymmetrical current. It is not asymmetrical. But that asymmetrical is more nearer to which one, sir? The asymmetrical is more during which period? Subtransient period. During subtransient period, this asymmetrical is more, sir. Then slowly, whenever this goes to zero, then we can getting the AC symmetrical current. Then after this point, sir, it's the AC symmetrical current. Then what is this one, sir? AC symmetrical current. AC symmetrical current. AC symmetrical currents. But what about this one, sir? Up to this point, this total current is which current, sir? Sir, AC symmetrical. It is asymmetrical currents. It is asymmetrical current. It is a asymmetrical current. It's asymmetrical current. Yes, students, you please come. It is asymmetrical current. After the DC component is completely falls to zero, then we can taken as a, this one is taken as which one, sir? Symmetrical component. Then this state is which state, sir? Steady state. This state is considered as a steady state. Okay. Once this DC component completely falls to zero, there is no any transient. Then there is no any transient term. Then this is considered as a which one, sir? Then this is the steady state. Then where you can measure where you can take up to one cycle or 1 to 2 cycles, sir. Up to 1 to 2 cycles, sir. This 1 to 2 cycles you are taken as which one, sir? This 1 to 2 cycle is taken as which period? Subtransient period. Yeah, this period is the subtransient periods. This is the subtransient period. The subtransient period is taken as a 1 to 2 cycle. During this only, it is a more decaying, sir. During subtransient period only, it is a more decaying, sir. Then it is 2 to 5 cycles, sir. If you take 2 to 5 cycles, from this point to this point, sir. If you take 2 to 5 cycles you can take. This 2 to 5 cycles, sir. This is 1 cycle or 1 to 2 cycles. 1 to 2 cycles you take. Then 2 to cycle. After 2 to 5 cycles, sir. 1, 2, 3, 4. This is 2 to 5 cycles, sir. This 1 cycle, 2 cycle, 3 cycle, 4 cycles, and it is up to 5 cycles. Generally, it is taken as which periods are? Transient period. After then 2 to 5 cycles, it is taken as a transient period. Yes, sir. It is a transient period. It is taken as a transient period. Yes, sir. It is a transient period. If you take this one observation, sir. If you take 1 to 2 cycles, I am taking once again, I am writing here. So please concentrate. It is a symmetrical current. It is a symmetrical current. Yes, sir. Yeah, this is 1 to 2. So this 1 cycle and this is the 2 cycle. You take up to this one. 1 to 2 cycles. It is the subtransient period. It is a subtransient period. But not exactly 2 cycles. It is 1 to 2. 2 to 5 cycles. 2 to 5 cycles means up to this you take. It is a transient period. It is a transient period. Okay, 2 to 5 cycles you take. Okay, this is taken as a transient period. Okay, sir. During subtransient period, there is a more decay. This component is more decay. This DC is more decay. During which periods are subtransient period? It is more decay. Then this period is taken as a transient. But remaining, this is up to 2 to 5 cycles means up to time constant 5 tau. Up to time constant is 5 tau. After 5 time constants, then system, whatever the DC component is there, that DC component will falls to 0. Then it consists of only AC symmetrical components. That means this is region 1 and this is region 2 and this is region 3, sir. Actually 1 to 2 cycles. 1 to 2 cycles is taken as which period, sir? Subtransient period. It is taken as a subtransient period. Yes, students, you please concentrate. What about 2 to 3 cycles or 2 to 5 cycles, sir? 2 to 5 cycles is taken as which one? It is a transient period. It's taken as a transient period. Yes, sir. After 5 cycles, from 5 cycles, the region is from 5 cycles, sir. From 5 cycles, it is taken as which one, sir? Steady state. You take the steady state. Okay, from 5 cycles, you take the steady state, sir. Yes, this is the observations from the waveform. How we are getting this waveform, sir? Whatever this waveform we are getting, this waveform. This is which waveform, sir? Total fault current. This is the total fault current waveform. This blue line, sir. This is the total fault current waveform. Which waveform? It's asymmetrical waveform, sir. It is a asymmetrical waveform. Why asymmetrical we are getting, sir? Because of this DC offset current. This DC offset current is added to this symmetrical component of current. Then AC symmetrical component of current. That's why we are getting. Once this DC offset current is falls to 0, then again we can get which currents are? We are getting the symmetrical fault current. This state is taken as a which one, sir? Steady state. This state is taken as a steady state. Yes, students, you please concentrate. Okay, this is the waveform of short circuit current on transmission line. This is a waveform of short circuit current on transmission line by combination of this is the total fault current, sir. This is the total fault current. The total fault current is transient current plus steady state current. Okay, that point you remember. Now we'll see. Yes, sir. That means, sir, the waveform. This is means this total is this is which current, sir? This current is which one, sir? Asymmetrical current. I already given this one. This is the asymmetrical current, sir. Yeah, this is the asymmetrical current, sir. Then after asymmetrical current, the DC current is completely decayed, sir. Here the DC current is completely decayed. When the DC current is completely decayed, the remaining current which one, sir? Symmetrical RMS current region. Then after this one, this is which state, sir? This is the steady state. This is the steady state. Okay, this is the steady state, sir. That means after this one, once the DC component completely falls to 0, then it is taken as a steady state. Clear, sir? But it is a which state, sir? It is a transient state. It is a transient. It is a transient state. But it is a transient state means it consists of two periods again. This is a combination of subtransient and transient. Subtransient and transient, sir. It is a combination of subtransient and transient. Yes, students, you please concentrate. It is a combination of subtransient and transients. Yes, sir. Okay, this is asymmetrical current. This is this offset current. But this is which one, sir? Symmetrical. Okay, these are the observation. If any three-phase short circuit fault is occur on transmission line, this observation is important. Now I want to calculate different values of short circuit currents. That observations, that calculations are very important for competitive point of view, but mainly very, very important for gate point of view. Yes, sir. The calculation of short circuit currents. The first one is sustained or steady state short circuit fault current, sir. What is the definition of sustained or steady state short circuit fault currents? The sustained short circuit current is the RMS value of the fault current at the line terminal which occurs after the DC component has decayed. That means when the DC component is completely decayed, whatever the RMS value of the fault current is there, that is nothing but a sustained or steady state short circuit current. That's why the steady state short circuit currents are I am representing as ISS. But it is a which value, sir? RMS value. It is RMS value of current. Then how to calculate, sir? You see this one. Generally, what is the steady short? After DC component is decayed to 0, then what is it consists only steady state short circuit current, sir. What is the instantaneous value of short circuit current, sir? Vm by Z sine of omega t plus alpha minus theta, sir. But I want only RMS value of current, sir. Then if you find it is a sinusoidal component, what is the RMS value of sinusoidal component, sir? Vm by that is maximum value by root 2. You divide with root 2, sir. This is the sustained or steady state short circuit fault current. Very important formulas. You please concentrate. Vm by this is the Z that you concentrate. This is Z, sir. I'm writing once again this one. You please concentrate. The steady state short circuit current ISS equal to, because you want it's RMS value of current, because of RMS value of current, I'm dividing with root 2. I'm dividing with root 2 because it's the maximum value, sir. This is the peak value. This is the peak value. I'm dividing with root 2 means that's why I'm getting Vm by root 2 Z. Okay, this is the steady state current, and it is the sustained short circuit current is the RMS value of the current at the line terminal, which occurs after the DC component has decayed. When the DC component is completely decayed to zero means, then it consists only which current, sir? Steady state current. Then what is the RMS value of this one, sir? Vm by root 2 Z. This is the peak value. I am dividing with root 2, sir. You please concentrate, sir. Yes, sir. Next, one more calculation. Initial symmetrical RMS fault current, sir. Initial symmetrical RMS fault current. I am talking about what is the very important formula, sir? Initial symmetrical RMS fault current, sir. What do you mean by initial symmetrical RMS fault current? It is RMS of AC component of current in subtransient period. Yes. The initial symmetrical RMS current is, it is RMS of AC component of current in subtransient period. Or it is also defined as RMS value of the AC symmetrical component of a short circuit current applicable at the instant of the short circuit if the impedance remains at the zero time values. That's why it is RMS value of AC component of current, or it is also called, it is RMS value of AC symmetrical components. Which is the symmetrical component of current, sir? This is only the symmetrical component of current. Again, what is the RMS value of this one? You can get the same formula. That's why I am writing this. Which one, sir? This is the initial symmetrical RMS current, sir. This is the initial symmetrical RMS current. I symmetrical. These calculations are very important, sir. This is the initial symmetrical component of current. It is a symmetrical component of current, sir. What is the symmetrical component of current? It is the RMS value of AC component of current. That is Vm by root 2 Z, sir. Okay, this formula is same. Now we are getting the same formula. But actually it is calculated during which time, sir? It is calculated during which period? Subtransient period. It is calculated during subtransient period. Then I symmetrical equal Vm by root 2 Z, sir. Okay, this is about initial symmetrical RMS fault current. Very important formulas. This I symmetrical equal to Vm by root 2 Z. Why you are taking by root 2 means because it is RMS current. Because it is a RMS current. Yes, students, all of you, good evening. It's very important formulas I am giving. You please concentrate. The next one is initial symmetrical short circuit apparent powers. But here I am not calculating any power calculations. Just I am giving what is the importance of this one. Initial symmetrical short circuit apparent powers. The short circuit power represents a fictitious parameter. During the planning of networks, the short circuit power is a suitable characteristics number. That means during the design of any circuit, mainly you can consider the short circuit apparent power is the main consideration. This parameter we can consider during the design of the or during planning of the any network. Okay, this about what exactly initial symmetrical short circuit apparent power. Sir, next one, sir. Very important calculations. Asymmetrical RMS fault current, sir. What do you mean by asymmetrical RMS fault currents? This term refers to a fault current magnitude at half cycle points. This is the half cycle. This is the asymmetrical current. I told already. The total current, the steady state current plus transient current is nothing but a which currents are asymmetrical current. This is the asymmetrical current waveform, sir. I told already this one. How we are getting this asymmetrical current waveform? By adding the steady state current and the transient current, we are getting this waveform, sir. Now I am calculating what is the asymmetrical RMS value of fault current. Yes, RMS of fault current. Then it is calculated half cycle point. At this point, the curve is highly asymmetric around the x-axis. Sir, students, you please concentrate. This is the x-axis, sir. Around the x-axis, during this period, during starting, at half cycle only, it is more asymmetric, sir. It is half cycle. Symmetrical means positive area equal to negative area. Then we can say that it is a symmetrical waveform, sir. But here, this is the area for negative. But this is the area for which one, sir? This is the area for positive. This is the area for positive. That's why during at half cycle only it is a more asymmetric. That's the reason why that asymmetrical fault current is calculated during half cycle. That is calculated during which periods of subtransient period only. Please concentrate, student. Asymmetrical RMS fault current is calculated during which period? Subtraction period. Sir, why you are calculating only at subtraction period? During that period only, the waveform is more asymmetric. But slowly, the waveform comes to, slowly whatever this waveform is comes to, then after it is completely decays to 0, then slowly it comes to which ones are? Symmetrical. It comes to symmetrical. That positive area equal to negative area. That is positive area equal to negative area. Slowly it comes to which ones are? Symmetrical. That's why this term refers to fault current magnitude at off cycle point. At this point, the curve is highly asymmetric around the x-axis. Now see, tell me sir, what about this asymmetrical fault current? What is this asymmetrical RMS value of asymmetrical fault current? The RMS value of asymmetrical fault current is calculated. The RMS value of asymmetrical fault current is calculated. It is a combination of DC component of current and AC component of current, sir. That is it is a square root of that is a RMS of DC component, that is RMS of DC component of current, DC component, that is whole square, plus RMS of AC components, RMS of AC component. It is a combination of both AC and DC, sir. RMS of AC component. You please concentrate. Okay, this is the asymmetrical current, sir. RMS of DC component current, RMS of AC component current. Then if you write the formula for what is this asymmetrical current, sir? This asymmetrical current, this I asymmetrical, sir. This asymmetrical component of current equal to what the RMS of DC component of current, sir. RMS of DC component is, it is a DC component means, you take this is Vm by Z. Vm by Z. Sir, sine of theta minus alpha. Sine of theta minus alpha. E power minus t by tau, sir. Whole square. Plus, what is the RMS of AC component of current, sir? That you calculated. Vm by root 2Z. It is a sinusoidal. That's why RMS value is Vm by root 2, sir. That is Vm by root 2Z whole square. Yes, students, you please concentrate. This Vm by the total DC component square. This is total is the DC component current. DC component of current. The RMS value is don't do by root 2, sir. It is not a sinusoidal. It is not a sinusoidal, sir. Don't, sir. You are done 1 by root 2 here, but why you are not taken root here? It is a DC component, sir. For example, 3 plus 4 root 2 sin omega t, sir. If 3 plus 4 root 2 sin omega t, what is the RMS value of this 3, sir? 3 only. The RMS value of this one is 3 only. What is the RMS value of this one, sir? You take 4 root 2 by root 2. Because it's a DC term. It's a constant term. For a constant term, average and RMS values are equal. If the constant is there, for a constant term, what is the average and RMS values are equal. That's why this total is considered as RMS, sir. Then I am taking RMS of DC component square. What is the RMS of this one? Vm by Z sine of theta minus alpha e power minus t by tau. Sir, sine of theta minus alpha is a constant value, sir. That depends on the theta and alpha. It's not a function. It's not a sinusoidal function. It's a sine of theta minus alpha. It's not a sine omega t term, sir. You please concentrate. Don't do by root 2 like that. Understood? The total DC component square plus RMS of AC component. AC component sine of omega t plus alpha minus theta, sir. Sine of omega t plus alpha minus theta means that term. What is sine omega t is there? That is a sinusoidal function. For a sinusoidal function, how to find the RMS values? That is maximum value by root 2. Maximum value by root. This is the Z, sir. That is whole square. Okay, this is the asymmetrical component. RMS value. This current is which one, sir? RMS current. This current is which one, sir? RMS current. That is the asymmetrical RMS current. Vm by Z sine of theta minus alpha e power minus t by tau whole square. Total DC component square plus, sir, for example, 3 plus 4 root 2 sin omega t is this, sir. How to find RMS value of this one? 3 square plus 4 root 2 by root 2 whole square you can write now. Like that I written. What is the total current? This component square plus AC current Vm by root 2 Z whole square. Like that I written. Clear, sir? Students, you please concentrate. Yeah, this is about asymmetrical component of current. RMS value of asymmetrical component of current. How we can calculate? RMS of DC component of current plus RMS of AC component of current. This square you can take. Understood, sir? Next. You please concentrate. Momentary current, sir. It's a momentary short circuit current. How to calculate momentary short circuit? It is asymmetrical RMS fault current, very close to instant of fault occurrence. Yes, sir. What is the asymmetrical RMS fault? Momentary short circuit current. It is asymmetrical RMS fault current, very close to instant of fault occurrence. Very close to instant of fault occurrence means you calculate at t equal to 0 plus. You calculate t equal to 0. This is defined at t. It is also which current, sir? Asymmetrical fault current. It is also asymmetrical fault current, but it is calculated at t equal to 0 plus. It is calculated at t equal to 0 plus. That you calculate. Then if you take at t equal to 0 plus means, if you take at t equal to 0 plus means, then what is the RMS current we can get, sir? Then it is asymmetrical current. What is the asymmetrical current, sir? Then momentary RMS current equal to momentary RMS current. It's a momentary RMS current. The momentary RMS current is also which current, sir? It is asymmetrical current. Momentary RMS current is also asymmetrical current. What is this value, sir? Square root of. Yeah, this you already know. Vm by Z, sir. Vm by Z. Sine of alpha minus theta. Yes, sir. This is sine of theta minus alpha. That is written. This is sine of theta minus alpha. E power minus t by tau, sir. This is whole square plus Vm by root 2 Z, sir. Vm by root 2 Z. This is whole square. Okay, this is also asymmetrical fault current. Momentary current is also asymmetrical fault current. You please concentrate. Asymmetrical fault currents. Momentary current is also asymmetrical fault current. Then this momentary current is also written like this. This is the momentary current at t equal to 0. It is calculated at t equal to 0. Yeah. If you calculated t equal to 0 means, if you calculated t equal to 0, sir, then what you can get? This momentary fault current equal to, then Im RMS equal to, this Im RMS momentary fault current is equal to square root of Vm by Z, sir. This Vm at t equal to 0 plus, it becomes Vm by Z whole square plus Vm by root 2 Z whole squares. Sir, how you taken this Vm by Z directly? That I will explain, sir. That is Vm by Z whole square plus Vm by root 2 Z whole square, sir. Then this momentary RMS current. This momentary RMS current equal to, sir, by simplifying this one we can get root 3. Then we can get this is momentary RMS current equal to root 3 by 2. I'm taking this one. Sir, by simplify this one, you take Vm by Z is common, sir. If you take Vm by Z whole square is common, this we can get Vm by Z. Then square root of, then what you get, sir? 1 plus 1 by 2. Then root 3 by 2. Root 3 by 2 into Vm by Z, sir. Vm by Z. But I am writing this current is momentary short circuit current. Sorry, momentary short circuit current. Im RMS equal to RMS value of momentary short circuit current. Shall you write like this, sir? Root 3 into Vm by root 2Z. Then this Im RMS equal to, this Im RMS equal to root 3 into, what is Vm by root 2Z, sir? This is a symmetrical RMS value of symmetrical currents. I into I symmetrical. RMS value of symmetrical current. That's a momentary, the RMS value of momentary short circuit current equal to, yes, sir, the RMS value of, I'm taking like this. Yes, sir, please correct this. RMS value of momentary short circuit current. Im RMS equal to, Im RMS equal to, how you can write, sir? Root 3 times of, root 3 times of, this is which current, sir? Vm by root 2Z, symmetrical current. This momentary current is very important consideration in the selection of circuit breakers. In the selection of rating of circuit breaker, Im RMS equal root 3 into Is symmetrical currents. But generally, we are not taken root 3 times, mainly in the circuit breaker selection. In general, this momentary current is taken as, in general, that momentary current is taken as, this I am writing here, sir. In general, how to consider this momentary current? this momentary current, RMS value of this momentary current equal to, instead of root 3, 1.732, generally we can take 1.6 times. For safety purpose, we are taking this one, 1.6 times of the symmetrical current. This is very important. During selection of circuit breaker, this calculations is important. Okay, IMRMS equal to 1.6 times of asymmetrical. In case of there is no DC component, then we consider that one Vm by R, because I given this is the approximate analysis. By approximate, I am getting 1.73. But it is a theoretical calculation. But practically, you can take IMRMS, the momentary short circuit current. Momentary short circuit current, it is RMS value, sir. We can take 1.6 times of the symmetrical. 1.6 times of the symmetrical. Now the question is, sir, at t equal to 0, why you taken this is as a Vm by Z direct? Sir, at t equal, this I am taking at t equal to 0 plus, or t equal to 0 plus I am, because why I am calculating t equal to 0 plus, sir? By approximation. It is asymmetrical RMS current, very close to instant of fault occurrence. That's why I taken at t equal to 0 plus. But why you taken this Vm by Z sin theta minus alpha e power minus t by tau is at t equal to 0 plus. Sir, how we are getting this one? Yes, sir, you please concentrate. Yes, I want to give that proof. Sir, what is we are getting, sir? This Vm by Z sin omega sin theta minus alpha. Vm by Z sin theta minus alpha e power minus t by tau, sir. At t equal to 0 plus means you take at t equal to 0, sir. At t equal to 0 plus means then what this value becomes, sir? That is Vm by Z sin theta minus alpha. Vm by Z sin theta minus alpha. Yes, sir. Let alpha equal to 0, sir. Switching angle is let alpha equal to 0. If alpha equal to 0 means what you can get, sir? Vm by Z sin theta. Vm by Z sin theta. At alpha equal to 0 means, that means, sir, during at fault condition, during starting, let x by r ratio is very high, sir. X by, for a transmission line, x by r ratio is very high. Or not only at the starting, generally for a transmission line, the x by r ratio is very high, sir. If x by r ratio is very high, then this theta is nearly equal to 90 degrees, sir. If you take theta is 90 degrees, sin 90 becomes 1, sir. Then I am replacing this Vm by Z sin theta minus alpha e power minus t by tau is nearly equal to Vm by Z. Is nearly equal to Vm by Z. Because theta equal 90 degrees sin 91, sir, then we are getting. I am assuming that alpha equal to 0. We are switching that switch at alpha equal to 0. Where alpha is the switching angle, sir. We are assuming that at alpha equal to 0, we are switching. Then it is calculated as Vm by Z. That's the reason why I replaced this one as, that's why I replaced Vm by Z sin theta minus alpha e power minus t by tau is replaced as a Vm by Z, sir. Is replaced as a Vm by Z. Clear, sir? Okay, this is the momentary RMS current. This is the momentary short circuit current. That value is measured as a RMS value. This is very important consideration in the circuit breaker selections. Yeah, actually, the circuit breakers ratings are also specified in terms of momentary current. This IMRMS equal to 1.6 times of asymmetrical. You take the 1.6 times. Sir, it's actually the 1.73, sir. But why you taken 1.6? Here I done some approximate analysis, sir. That's why it's a theoretical calculation. But practically you can take this 1.6 times of the asymmetricals. Clear, sir? Students, you please concentrate. The next one is the maximum momentary short circuit current, sir. It's the maximum momentary short circuit current. What is the maximum momentary short circuit current? It is the highest instantaneous value of fault current. This one. The highest instantaneous value of fault current is nothing but a maximum momentary short circuit current. This is the highest instantaneous value of current. This total current is taken as a maximum, this total current, sir. It is the highest instantaneous value of fault current. Highest instantaneous value of fault current. Then what is the maximum momentary fault current? Short circuit current, sir. The maximum momentary short circuit current, IMM equal to, this is a IDC at t equal to 0 plus IAC at t equal to 0. IAC at t equal to 0. It is measured as IDC at t equal to 0 and IAC at t equal to 0. Then generally what is maximum momentary current? It is the maximum. You take the maximum value, sir, not RMS value. It is the highest instantaneous value of fault current, and it is the maximum current. It is the maximum current. That's why no, don't take the RMS. But previous cases, all those values are which values, sir? It is the RMS value. It is the asymmetrical RMS current. It is the asymmetrical RMS. That's why momentary short circuit current is the RMS short circuit current. But maximum momentary current is not a RMS current. It is a maximum current. What is IDC at t equal to 0, sir? What is IDC? Just now I calculated this term. What is this term? This is the IDC, sir. This is the IDC. This term is the IDC, sir. What is IDC at t equal to 0? By approximate Vm by Z, sir. I am calculated as Vm by Z. Then IDC at t equal to 0. This is Vm by Z, sir. What is the maximum AC current, sir? What is the maximum AC current? It's a Vm by Z only. It's a Vm by Z only. Then what is IMM? You can get the maximum momentary current equal to what you can get, sir? 2 Vm by Z. It's a 2 Vm by Z. Now I am doing some small modification here, sir. The maximum momentary current equal to multiply with root 2 and divide with root 2, sir. Then 2, this we can get Vm by Z. I want to get one formula. That's why I am doing like this one. Multiply with root 2 and divide with root 2, sir. Then what is the maximum momentary short circuit current? The maximum momentary short circuit current equal to IMM equal to this gives which value, sir? This gives which value? That is a steady state short circuit current. That is 2 root 2. This is a 2 root 2 symmetrical short circuit current. Symmetrical short circuit. This is a symmetrical current. It is RMS current. This is which current, sir? RMS current. Here 2 root 2 times. That means the theoretically its value is 2 root 2 means, sir. What are the 2 root 2 values, sir? That is 2 into 1.414. Then you can get 2.828, sir. But this is the theoretical calculation. But I calculated by approximation of this one, sir. But practical, this is a theoretical calculation. But practically, the momentary current, this current is also called, the maximum momentary current is also called making current, sir. It is the making current. This maximum momentary current is taken as a making current. In the case of circuit breaker, it is taken as a making current. Then for making current in circuit breaker design, what are the making current, sir? The making current is generally considered as IMM equal to this I making equal to, how we can consider, sir? Instead of 2.828 times, we can take only approximately, we can take how many times, sir? 2.55 times. This is a symmetrical current. 2.55 times of the symmetrical current we can take. This is the making current. That's why in the case of circuit breaker, the making current is not RMS current, sir. It is the maximum current. Making current is the maximum current. But the breaking current is which one, sir? This is the RMS current. The breaking current is the RMS current. That is the 1.6 times. But the making current is 2.55 times of the symmetrical current. 2.55 times of the symmetrical current. Yes, students, you please concentrate. Okay, this is the calculation of maximum momentary current. Every calculation is important. Who are the gate aspirants are these? It's very, very important for gate aspirants and also for ESE aspirants. Okay, this is a maximum making current equal to 2 root 2 times of the symmetrical current. It's a symmetrical. That symmetrical current is which current, sir? RMS current. Understood? Okay, this is about maximum making current. This is which one, sir? This is which current, sir? Momentary short circuit. But this is the maximum momentary current. Yes, sir. Then this is in circuit breaker. Yes, sir. This calculation. These are the calculation of short circuit currents. But here I want to give some note points, sir. This is very important. Listen, please, students. All of you concentrate. Here I want to give some note point. Sir, what is the total fault current, sir? The total fault current IF equal to Vm by Z. Yes, sir. The total fault current IF equal to Vm by Z. Sine of, what you written, sir? This is Vm by Z sine of theta minus alpha. E power minus t by tau plus Vm by Z sine of, that is sine of omega t. Take minus is common. That is also theta minus alpha. Take the minus is common. That is theta minus alpha. Actually, it is a sine of omega t plus alpha minus theta. But I taken minus is common. Okay. This is which current, sir? Transient current. This is the transient current. What is this current, sir? Steady state current. Steady state currents. Now, I want to explain this note in case 1. In three different cases, I want to explain. Now, the question is, yes, sir. The conditions for no DC transient at the instant of fault. During the transient, during the fault, if there is no any transient, then which condition must be satisfied? Which conditions must be satisfied? Okay, that means that is the conditions during no transient. The conditions for no transient during fault. That is, I am calculating conditions. What are the conditions? Conditions for no transients. Conditions for no transient. No transient during fault condition. During fault. That means if there is no transient will occur during the fault, means which conditions must be satisfied? The conditions for no transient during fault. Then no transient means which ones are the transient current must be 0. The transient current must be 0. The first I am giving for the transient current must be 0 means then which term we can equate to 0, sir? That is sin theta minus alpha equal to 0. If sin theta minus alpha equal to 0, then that means sin theta minus alpha equal to 0. We can equate. If there is no transient means then this term must be equal to 0. Sin theta minus alpha equal to 0. Sin theta minus alpha equal to 0 means what is sin theta minus alpha equal to 0 means? Then theta minus alpha equal to 0. Then theta minus alpha equal to 0. Then what is theta equal to, sir? Alpha. Theta equal to alpha. That is the meaning. That means there is no transient. This case 1 I am giving like this, sir. If there is no transient, then what is the condition? If there is no transient during fault. Case 1 I am giving during fault. If there is no transient during fault means the transient term we can equate to 0. When this term equal to 0, sir? If there is no transient means we want to make ITR equal to 0. Then only there is no transient current. Then ITR equal to 0 means in this one which term we can equate to 0, sir? This never be 0 and this never be 0. Then only this term we can equate to 0. Sin theta minus alpha equal to 0. If sin theta minus alpha equal to 0 means what the theta equal to? That means if the impedance angle of the transmission line is equal to switching angle, then there is no transient. That means we can make the switching action is equal to impedance angle. We can switch that switching action is at alpha equal to theta. The switching angle, that means if switching angle is equal to, if the switching angle is equal to impedance angle of line, then there is no transients. Yes, sir. Next, this is the condition for no transients. Case 2, sir. Condition for maximum positive transient. That is condition for maximum positive. I want to find condition for maximum positive DC transients. DC transient, you write as a DC transient at the instant of fault, sir. At the instant of fault. Yes, sir. Condition for maximum positive DC transient at the instant of fault, sir. Then at what condition we can get the maximum transient? We can get the maximum positive transients. Understood? If there is no transient means I am taking ITR equal to 0. Then if maximum transient means ITR must be maximum, sir. ITR must be maximum. When this term is maximum, sir, sin theta minus alpha must be maximum. Is equal to maximum. What is the maximum value of sin theta minus alpha, sir? 1. Then if theta minus alpha equal to 1 means what is the theta, sin theta minus alpha equal to 1 means what theta minus alpha are pi by 2. Then what is theta? You can get that alpha equal to pi by 2 plus theta. That means if the switching angle equal to 90 degrees plus impedance angle of transmission line, then if you switch at that instant, then you can get the maximum transient at the instant of faults. We can get the maximum transient at the instant of faults for alpha equal to pi by 2 plus theta, where theta is the impedance angle of transmission lines. Clear, sir? What I am telling. If there is no transient, this condition must be satisfied. If there is a maximum positive DC transient, these conditions. If alpha, if you switch that, if you make the switching action is at alpha equal 90 plus theta, then during that condition we can get the maximum transient. But it is a positive DC transient. That means because I taken the sin theta minus alpha term, this is the positive. When this term becomes negative, then we can get the maximum negative transients. We can get the maximum negative transition. Is a maximum, that condition for maximum negative DC transients. Here I am giving case 3, sir. Condition for maximum negative DC transient at the instant of faults. At the instant of fault. Yes, students, you please concentrate. What is the condition for maximum negative DC transient at the instant of faults? Then when this value becomes, but it is a negative maximum. Negative maximum means sin theta minus alpha must be maximum negative. Maximum negative. What are the maximum negative values, sir? -1. Then theta minus alpha equal to how much, sir? It is sin theta minus alpha equal to -1 means what is the theta minus alpha, sir? You take sin of -90 equal to -1. This is what is theta, sir. From this one, what is theta? Or theta or alpha equal to how much, sir? This alpha equal to pi by 2 plus theta. We can get alpha equal to, in negative maxima is also occur at pi by 2 plus theta. Yes, sir. This alpha equal to theta minus, previous case is which one, sir? Alpha. You please concentrate. The previous case, I am calculating alpha. Please concentrate. This is wrong. Sir, what is alpha, sir? Alpha equal to here. Alpha equal to, this you write theta minus pi by 2. What is alpha? This is theta minus pi by 2. You bring this side alpha, this theta minus pi by 2. If it is satisfied, then you can get the maximum positive DC transient. Then if it is satisfied, what is alpha? Pi by 2 plus theta. Yes, students, you please concentrate. It is a pi by 2 plus theta. The maximum DC transient, positive DC transient is occur at theta minus pi by 2. Theta minus pi by 2. But maximum negative DC transient is occur at alpha equal to pi by 2 plus theta. That is theta plus pi by 2. Okay, these are the observations. These three conditions you remember, sir. This is the case 3. This I written as a case 3. Yeah, these three cases, sir. If there is no transients means alpha equal to theta. If there is a positive, maximum positive DC transient means alpha equal to theta minus pi by 2. Sir. Alpha equal to, what this one, sir? Theta minus pi by 2. It is the condition for maximum negative DC transient occurs at alpha equal to pi by 2 plus theta. If you make the switching at pi by 2 plus theta, 90 plus theta, there is a maximum negative DC transient. Yes, sir. Okay, these are the observations. Okay, that one note you remember, sir. One more note I am giving. You please concentrate, students. Generally for A, I taken A phase is reference. I taken A phase is reference. A phase is reference. A phase is reference. If A phase is reference means what is the, this fault current I got, sir? This Vm by Z sin of which one, sir? Sin of theta minus alpha e power minus t by tau. E power minus t by tau. Then plus Vm by Z sin of omega t plus alpha minus theta. If you take the negative is common here, we can get theta minus alpha. Yeah, this is one. But what about for B phase, sir? B phase. This is the A phase fault current. The A phase fault current. If you want to write B phase fault current, what is B phase, sir? B phase fault current. B phase means, sir, how you can write, sir? B phase. Then the fault current IF equal to some constant K into e power minus t by tau plus Vm by Z sin of omega t. Yes, sir. So sin of omega t. This is alpha. What? It is a B phase is the phase difference between A phase and B phase is how much, sir? 120 degrees. It's a 120 degrees. The phase difference between A phase and B phase is how much, sir? It is a 120 degrees you can write. Yes, sir. That is this is which one, sir? It is omega t plus alpha minus theta. It's omega t minus alpha minus theta. That is sin omega t minus 120. Sin of omega t minus 120 plus this how much, sir? We are getting. This is alpha minus theta. Vm by Z sin omega t minus 120 plus alpha minus theta. The phase displacement is how much, sir? It is 120 degrees. It is 120 degrees. Then from this one, you calculate K value again. Then K value will change, sir. For A phase reference, I taken this one. This is a DC component. This is the DC component for A phase. Then you take the for B phase, I am calculating, sir. K into e power minus t by tau. That is Vm by Z into sin of omega t minus 120 plus alpha minus theta. Then K value changes. Then according to that DC term is also changes. Apply the initial condition, then you can calculate. Then what about for C phase, sir? If you write for C phase, then what is IF, sir? This IF equal to K into e power minus t by tau plus Vm by Z sin of omega t minus 240. The phase difference is 120. With rest, or you take omega t plus 120 or minus 240 plus alpha minus theta. Yes, sir. Now from this also we can calculate what is the K value and what is the DC value. That means what is the observation here, sir? That means the value of IDC will differ from one phase to another phase. For all the cases, the DC term is not same, sir. Understand? The value of DC term will differ from one phase to another phase. That I am telling that. Why, sir? Because of this 120 degrees, the value of K will be changes. The value of K will be changes. Understood? Students, you please concentrate that. Yes, sir. So, okay, this is minus 120, this is minus 240. Then if you take the K value, then apply the initial conditions at T equals. That means, what is the observation here? That means, here final observation I am giving, sir. That is, DC component, the value of IDC, will differ from one phase to another phase. Will differ from one phase to other phase. One phase to other phase. Because of phase difference is 120. For A phase, what is the directly I am giving, sir? For A phase, for phase A, what is the IDCA, sir? Just you calculated already. This one Vm by Z sin of alpha minus theta. This Vm by Z sin of theta minus alpha. Calculated already this one. Sin of theta minus alpha e power minus t by tau. Then similarly, what is for B phase? IDCB, sir. The DC component of B phase is what you can get? Vm by Z. This one is we can get Vm by Z sin of 120 plus theta minus alpha e power minus t by tau. Then what is IDC C phase, sir? IDC C phase equal to Vm by Z sin of this we calculate minus this is plus 240 plus theta minus alpha plus 240 theta minus alpha e power minus t by tau. Okay, this we can get. Sir, how you calculate this IDCA, IDCB, IDCC, sir? By taking this initial conditions. In this case, you apply the initial conditions. Apply the initial condition at t equal to 0. At t equal to 0, what is this IF of J? equal to 0. Then you can calculate K value. Then you can get K value is what you can get, sir, Vm by Z sin of omega t minus 120 plus alpha minus theta. Understood? Then you take, for example, I am calculating for B phase. Just I am giving one calculation for B phase. For B phase, just how to calculate for B phase. So whatever the A phase I given same calculations, sir. Then what is for fault current with respect to B phase, sir? This is K into e power minus T by tau plus Vm by Z sin of omega t plus sin of omega t minus 120 plus minus 120. What I written, sir, here? Alpha minus theta. It's alpha minus theta. This is alpha minus theta. Then at t equal to 0. At t equal to 0 plus. You take this is equal to 0. Sir. This is equal to 0. Then if it is equal to 0 equal to K plus Vm by Z sin of minus 120 plus alpha minus theta. Then from this what the K values are? The K value equal to minus Vm by Z sin of 120 minus 120 plus alpha minus theta. Then you multiply with the negative sign, what you can get, sir? Vm by Z that is sin of if you multiply with this is 120 plus theta minus alpha, you can this I written, sir. Vm by Z sin of theta minus alpha e power minus. Then you substitute K value here, sir. You substitute K value here. If you substitute K value here, what you can get? Vm by Z sin of 120 plus theta minus alpha e power minus T by tau. Sir, just you will see. That means what is the observation here? Based on the phase, the DC term will change. From phase to phase, the DC term will change. That point is very important. That observation is important. Okay, this about in detail the short circuit fault analysis calculation on a 3-phase transmission line. See, I calculated for only one phase, sir. For remaining phases, you can write directly. Why? Because there is a 120-degree phase difference. But you can calculate DC term again. I calculate B phase DC term. Then you substitute here, sir. You substitute K value here. Then what you can get? For what is IFB, you can get, sir. IFB equal to Vm by Z sin of 120 plus theta minus alpha e power minus T by tau plus what is this term, sir? Vm by Z sin of omega t minus 120 plus alpha minus theta. Okay, this you can calculate. I am writing separately. There's no problem. Yes, sir. Take one more page here. Then if you want write IFB, sir. What is IFB? You can get that is Vm by Z sin of 120 plus theta minus alpha e power minus T by tau plus Vm by Z sin of omega t minus 120 plus alpha minus theta. Yeah, this is the B phase. Then similarly, if you want write what is C phase current? IFC equal to. Similarly, calculate Vm by Z into sin of 240 plus theta minus alpha e power minus T by tau plus Vm by Z into sin of omega t minus 240 plus alpha minus theta. Like this you can calculate the A phase current and C phase currents. Sin of theta minus, this is what you can get, sir. Sin of 120 plus theta minus alpha. This is correct. Okay, this is the calculation of fault currents for B phase and C phase also. Just to calculate 120-degree phase difference you consider. It's a 3-phase system, it's a balanced system. You consider 120-degree phase difference, then you can take like this. Understood? Okay, students. Okay, this is about in detail analysis of 3-phase short circuit analysis on transmission line under no load condition. You please concentrate. Okay, students, follow me on Unacademy using this link about more updates about my videos, and download our Unacademy learning app, and during unlocking of the app, use my promo code Babu10. Follow all my videos, not only in YouTube. There is a special classes also there. There is a free special classes are there. Different concepts I am explaining. You follow that concept. Who are preparing for GATE and ESE and PSUs, that is more useful for you to crack any competitive exams. Yes, sir. Yeah, this is our Unacademy GATE Telugu Telegram channel. Whatever the concepts we are explaining, all those concepts we are uploading as a PDF material for your reference purpose. This is India's #1 study channel, sir. Creatics GATE, Electrical, EC and Instrumentation. Unacademy GATE, Mechanical Engineering. Unacademy GATE, Civil Engineering. Unacademy GATE Telugu. Unacademy SSC JE. Unacademy Computer Science. Unacademy GATE Questions. Electrical Junction. Engineering Padashala. GS Techno RRB and SC. All these India's #1 study channels. Please subscribe all these channels. You can get the more updates on different subjects, on different concepts to crack any competitive exam. Yes, students, thank you. In tomorrow's session, we will continue with new concept with respect to fault analysis only. After completing tomorrow's session concept, then we can solve the problems on fault analysis. That is very important for preparing for GATE point.